I'm supposed to put 3 screenshots in there? Last time I did that,
What put you on the riding portion?
explain key points when it has happened.
He wants you to like dap it down, like edit in things on the actual picture.
Evidence this week. Literally.
That's the last one I forgot.
Yeah.
I'm probably gonna apply with Dr. Lee.
Oh, here?
Yeah, just as a backup. So, do I really want to go to graduate school at Vanderbilt?
Yeah. It's a lot of things, like, and so, like, I don't know. I guess I answered no.
What do you have in the class now?
But literally, the opportunity came up in, like,
Yeah, you know. Hey, you already said
Yeah.
he's been, like, talking about it.
89
Since
points.
the start of the semester, but then he brought up details. So, I made more mad answer. Oh, no, because I got it. I was like, oh, dude, that's a lot.
If you're going to be doing a PhD, you really want to be doing it with someone that needs you to answer whether or not you're doing a PhD with them.
It's mainly like put it all like on the deeper stuff though, like down here. I'm not just like I want to be stop. At least right now. That's just a big gamble. And
Yeah, I feel bad for Mac because he really
look right here.
he worked 2 things on the paper.
What did you make?
Made a 6 out of 8. And a 3 out of 4 on the progress.
Oh, I got a 1 second value.
Well,
How am I supposed to be ethical if I'm morally relativist anyway?
yeah, I
There
mean,
was some check marks this time.
only 50 in absolutes.
Did it say anything about best not completing something? Figure design could be improved. Figure design can be improved. What the fuck? That's design. I put a picture in there.
This is magic. How is this front cover page being held
For
on?
it to be so, for it to not be a report,
Is it
lab
like
report,
adhesive?
it's a fucking lab report, I tell you that. Yeah, you gotta do step by step. Almost just like that.
The reason I got a 6 was because I had bad grammar.
Go home and sniff one every night?
Yeah, I did.
You know, he tells us it's not supposed to be a lab report.
Yeah.
And then you make it more informal.
That really. That's something you had to consider that school.
I'm for sale if it means I get a better grade. My body's already.
There are a few memos down here.
Oh man, it's 3 weeks till I got the memo.
I'd like to make a few comments about those memos in a minute, but let me first talk about where we are today. So we're at week number 7 here.
2:30.
What you make on the right?
You just finished week 6. Your partner or you wrote
Figure design.
your last memo. Person A on the team is written your last memo for the semester. This week is you'll turn in your notebooks. And so we're going to work this week on what is known as the pulse width modulation idea. Again, it's dealing with a timer. We're going to introduce basically one more register to deal with to change the characteristics of the signal. And I'm just going to take a wild guess that somebody next door has just shut off the AV system. So we're stuck for a few minutes. I have to wait for 51 seconds for it to be ready to be turned back on.
How was your weekend?
My weekend was great. I went to the football game. Saw some, I didn't see any of you guys. I did see one of our graduate students there. Use a little bit of rain. Fifteen more seconds. We're back. All right, so we're going to work on the pulse width modulation this week. I do want to point out that next Monday we will have a meeting, but there's no lab next week because next week we have fall break, Thursday and Friday. So we will have no lab meetings that week. Probably some of you may ask, well, if I'm around, can I get in the lab, get ahead? My suggestion to you is, get one of these things and go to your GTA and say, or your TA and say, hey, that's not my decision, okay? They're the ones who really control the lab, and so you can work with your TAs about that. Tell them that you'll give them a good teaching evaluation at the end of the semester. All right, but there will be no lab meetings Tuesday, Wednesday, Thursday. We will have a brief meeting on Monday. We're going to talk about written communications as it applies to this assignment that it will be due on October 25th, the experimentation report. Some of you may have had classmates ahead of you who maybe talked about their midterm design report. It was a full report talking about the design, how it's supposed to work, and how they tested it to show that it worked. Okay, so we've scaled back the assignment. It's not a full design report, it's just an experimentation report. So I'll talk about that next Monday. Okay, so we've had several cycles of these memos, A1, B1, and then A2. And something that has been a recurring theme that has come up in the ethics case study, I'd like to talk a little bit about for just a few minutes. And so this is regarding engineering ethics. Engineering ethics case study. One of the things we do, you study this case study about something that went wrong in some sort of engineering problem, and I ask you to consider what was the dilemma and how the IEEE Code of Ethics might apply. And a number of students would have raised this thing. They said, well, there's a conflict of interest. Conflict of interest. And what I have discerned from reading your report is that there's not a good understanding. Many of you may not understand really what is a conflict of interest. And you'll see, if you mention conflict of interest, I'll probably say, no, you're wrong. This is not a conflict of interest. This is what I would call maybe conflicting interest. Or competing interests. Competing interests. Now, competing interests and conflicting interests are not the same thing as conflicts of interest. Let me give an example of competing interest and conflict of interest. So this weekend, our boys are going to Florida. And we want to win. these are competing interests. So one or the other, but these are not conflicts of interest. I'm a horrible artist. This is just to give you an idea. You know who that is? That's the ref. The zebras. Okay. So he's the ref. I hope I've drawn his stripes the right way. I think they go vertical. Okay. This is the referee. The referee is a Florida alum. He's a Gator. Is that okay with you?
No.
He has a conflict of interest. Okay? Our boys don't have conflicting interests. Like a conflict of interest. The Florida players don't have a conflict of interest. They have competing interests. The guy in this story who has a conflict of interest is the ref. He has no business being a referee for this game. Okay? Let's bring this a little bit closer to engineering. Okay? You are the design engineer. And you are designing a circuit. Later on this semester, you're designing a circuit, and you've got to pick a part. Okay, you got to buy it from somebody. You got to choose a part. And there's two companies out there. Company A wants you to buy their resistors. Company B also wants you to buy their resistors. Okay? These are competing interests. Okay? They're competing interests. But these are not conflicts of interest. But now I tell you, Company A owns this company, is owned by your uncle. Uncle Bob owns Company A. Who has a conflict of interest?
You do.
You do. That's right. You have a conflict of interest. You're supposed to be making decisions just based on which resistor is better. Maybe a better price or whatever. But you know you're going to see Uncle Bob at Thanksgiving. He's going to give you grief. He said, "Why didn't you pick my company?" And you're saying, "Uncle Bob, I'm trying to enjoy my turkey here." You have a conflict of interest. You need to go to your boss and say, "Hey, our regular vendors are this guy and this guy, but I have a relative who owns this company or has a financial share of this company, or my mom has a share, or I have a share. I should not be making that decision. I have a conflict of interest." There are competing interests, but this, I, the design engineer, would have a conflict of interest. Okay, any questions about conflicts of interest? Okay. All right, very good. We understand that better, I hope. So we're going to do this week what is known as pulse width modulated waveform generation with a keypad selectable duty cycle. In reading the memos last week, I kind of get the impression that everybody's doing pretty well. You got your stop, for the most part, most people got their stopwatches working, which means they understand the programmable timer, they understand how it can generate an interrupt, You can write a piece of software that services that interrupt, updates the digits, that's good. So your programming skills are really warming up, doing well. You can control the timer. I would like to have seen some more evidence of that in the logic analyzer screenshots. But at least you're claiming that you can control it. So that means your keypad interface at least is working for at least 2 buttons. And so this week we would like to control something else with some buttons with the keypad. So maybe that's working. And again, we're going to use the timer, but this time the timer, instead of interrupting us and asking for service, the timer is going to control the output of a pin. It's going to turn that pin on and off, on and off. Okay? So again, it's still the programmable timer, but we're going to just set up the timer to do something slightly different. And we're going to use this waveform in the future to drive a DC motor. Now, I'll give you a little bit of a peek ahead. What we're doing is there's a motor that has embedded within it a tachometer. It produces a signal that we can measure, and we can measure that signal, and we'll get some sort of idea of what the speed of the motor is as it's turning. And then your keypad interface is, you got a keypad right here that you're controlling, sending signals back and to the keypad, reading signals back from the keypad, and from that you will decide what desired speed is. And then so today what we're going to do is we're going to generate this waveform. This week we're going to generate this waveform whose characteristics are controlled by the keypad. Okay? And then on another week we're going to amplify this signal to a level where it can drive the motor. So we're kind of gradually working our way around it. All right, so what is a pulse width modulated waveform? I think you may have seen this before, but for those who may not, here's a brief introduction. It's a periodic signal. That means it does the same thing over and over again. However, there is some characteristic that can be varied, and we're going to vary the duration of the waveform. And so when we're saying it's a pulse width modulated signal, we're going to vary the waveform, the on time. We're going to hold the period constant, but the pulse width is going to change, and we're going to have a change and have a desired effect. Now, PWM is used a lot to drive things like motors in industry. You can lower the illumination in the room here. Those of you who have done maybe RC hobbyist work, this is a picture of a RC radio control servo. And the way it works is there is a radio receiver that receives ear commands from the joystick, and out of that receiver will come a pulse width modulated signal that looks kind of like what you see here in this blank picture here. And what this signal has is a 20 millisecond period. That means for the time from here to here is 20 millisecond. Right now here we're showing roughly a 1 millisecond pulse width. And then what we can do is we can vary you can either vary the width of this narrow pulse, or you can reduce the period from here to here. Either way, what's going to end up happening is that the average voltage of the signal is going to be proportional to the amount of time the signal is on, divided by what we call the period of the signal. And so what will happen in an RC servo is that this signal characteristic will change, like the pulse width will change, or the period will change. And then there's a little controller here inside this box. It's a microcontroller, just like what you're working with. It's a lower level microcontroller, but its job is basically to study the position of the motor. There's a potentiometer buried inside here. And what it will do is this thing will generate a pulse width modulated signal to turn a tiny little motor inside here. And that motor will turn this arm, which causes your airplane to go up or down, or turn to the right or turn to the left. And then this microcontroller is watching as this little arm here moves. It turns the potentiometer, and it says, oh, the potentiometer value's finally reached the value that I want it to be at, and then I'll stop. And then it shuts off this signal. Okay. Here's some examples of pulse width modulated waveforms. Okay. And all three of these waveforms have the same switching frequency. We call it, or the period. We call this the PWM period, from here to here. This time here is called the on time. This is called the off time. literature, sometimes we call this the active time, and this is the inactive time. Of course, you can also say, well, does my active always have to be high? Could I change it so that the active is low? You can. You can reverse this and call this the active time and call this the inactive time. But basically, what we're going to do is we're going to hold the total period here constant, and we're going to vary this pulse width. And the ratio of that pulse duration normalized by the period is what we call the duty cycle. So this is one definition of duty cycle. This shows a 25% duty cycle signal. It's on 1/4 of the time and it's off 3/4 of the time. This is a 50% duty cycle signal, and this is a 75% duty cycle signal. Now, if you do a little bit of Fourier series analysis of a periodic waveform and just calculate the DC component, the A0 component, say in Fourier series, you discover that the average value of these signals is proportional to the duty cycle. So if this signal here has a maximum value of Vmax, then the average value of the signal is going to be 25% of Vmax for this case. Here, because we're on half the time and off half the time, the average signal is just half of the maximum voltage. And then here, in the last case, the average voltage is going to be 75% of the maximum voltage. All right? So these are examples of pulse width modulated signals. All right, we've been introduced to the timer, and what we did last week with the stopwatch is we just generated a periodic interrupt. And when that interrupt happened, we said it's time to update the digits, tenths digits, units digits, and so forth. Okay, a counter, we just updated a counter. So what you can do, however, is you can also use the timer to control an output pin. And you can control the output pin multiple different ways. You can, for example, create a waveform, a signal waveform. We're going to create a waveform where some characteristics can be changed. You've already been introduced to this register, the auto reload register. You calculated what the auto reload register needed to be, as well as the prescale, so that every 1/10 of a second you updated the 10th digit. This week, we're going to introduce just another register, capture compare register. And it's going to basically allow us to vary this pulse width. So I just kind of jump to the end here. This time period is controlled by the auto reload register, but this period here, this on time, is going to be controlled by what is known as a capture compare register. And so you'll vary this. The basic idea is when we press a button on the keypad, you'll change this number, and this duty cycle will change. We won't change this part. We'll keep it constant. So that's kind of the high-level idea, is that we're going to vary this number, and it will cause the duty cycle to change. So that's one thing that we can do, is we can generate a pulse width modulated waveform. We can also generate a single shot, or one shot, and then just shut off. Later on in the semester, we're also going to say that rather than outputting out to a pin, I could be monitoring a pin, and when something happens on the pin, I can check the time and see how much time elapsed. But that's something that we're going to do later in the semester. Okay, so what have we done so far with timers is illustrated right here, this part. Okay? You picked a clock. The default was 2 megahertz roughly. You could use a 16 megahertz clock if you want to. You made sure it clocked. You set up your prescaler, your auto reload register, and then periodically, 1/10 of a second, it generated an interrupt. Okay, that's what you did last week. This week, we're going to basically use this, but we're going to introduce another register. It's called a capture compare register. And so this counter here is going to observe or keep track of its count and compare it to two things. It's going to compare it to the auto reload register and also the capture compare register. And then what it's going to do is it's going to, when something happens, it's going to change the state of an output pin. It's going to change the state of an output pin. If I kind of zoom into just this part right here, that's what the next slide is. Okay? We have the auto reload register and the counter, which we've done last week. We used that for doing the stopwatch. This week we're going to add a capture compare register, and these events. So what we're going to do is we're going to use it in pulse width modulation mode. You could generate a one pulse, and what it would do is it says, you tell me what the auto reload value is. Here the auto reload value is 7. And so what we're going to do is we're going to generate a signal with this period. And then when the count is less than this value, capture compare register, CCR, then I'm in one state. But once the counter exceeds CCR, then I go to the other state. And so here in blue, you see when the count is less than capture compare register, I'm in one state. But as soon as the count goes over CCR, then I switch to the other state. Then when the counter reaches the auto reload register value, I start all over again. You see the count goes from 0 to 7, hits the auto reload, and then starts all over again, 0 to 7. But in between, when the count reaches whatever number I put into this register, in this case 3, it's going to change state. Okay, so we're just adding one more register. We're going to tie that register value to your keypad. So right now, hopefully you've got your keypad working. You can identify any one of 16 buttons. You just want to map a button press to a number. And that number will go here. And hopefully this waveform will change its duty cycle. Now, there are still, however, a bunch of flags to deal with because now we're dealing with hardware again. And so this part, let's come back here. We're going to now turn our attention a little bit to this area right here. Take a look at the output stage. We're going to take a look at this, and we're going to add this here. And that's what this picture is. So again, here's the counter. It's going to be compared to auto reload, and every time it reaches auto reload, it's going to go back to 0 and start counting up again. But it's also going to keep its eye on the capture CCR value, and it's going to change state. Now, we need to tell it what to do with that information. As I said, you can generate a single pulse, or you can generate PWM. You had to decide what is the mode you're going to use, and there's going to be a register. We're going to talk about it in a few minutes. There's some bits that you have to choose so that it generates this pulse width modulated signal. Now, once you generate the pulse width modulated signal, you got to decide, well, is this signal going to be considered active high or active low? So again, there's a polarity that you can select, and it's going to be in another register. So we're going to talk a little bit about that. So you could say, well, I'm going to generate this signal, or I'm going to generate its complement, and I'm going to call this part active, or I'm going to call this part active. So there's a lot of different ways you can set this thing up. Technically, we can also say that I'm not going to call, for example, time t equal to 0 to be right here. I could say I'm going to choose time t equal to 0 to be in the middle of the pulse, and I'm going to adjust the width on both sides. A lot of different flavors about ways that you can generate a pulse width modulated signal. Lots of flags to keep up, just a lot of options. It's just like buying a car. There's a lot of options that you got to decide what color you want. All right. Now, in addition to generating the output polarity, you still have to. There's another flag that has to be set so that the thing actually gets out to the output. All right. This is considered a type of alternate function. Remember, the general purpose I/O pins could be inputs, could be binary inputs. They could be outputs, digital outputs. They could be analog inputs, which we'll see in a few weeks, or it could be alternate functions. And there's a lot of different alternate functions. Not every pin can have the same alternate function, but being driven in analog as a PWM mode is one of the alternate functions. And you'll recall a few weeks ago when you were first setting up digital I/O, you had to say, well, I want this pin to be an input and that pin to be an output. You did it through the mode register. And so this week you're going to revisit the mode register. You've seen it before, but you got to go back a few weeks, go back to the mode register and set it up for an alternate function. And as I said, depending on what pin you have, like PA5 or PA6 or PA7, you're going to have some default functions, but the alternate functions vary from pin to pin and from device to device. This week, what we would like to use is PA6, port A pin 6, because we want to use timer 10, channel 1, to do a pulse width modulated signal. Now, as I said, there's so many different choices. You could do a timer output, you can do a serial port, you can do an LCD driver, so on and so forth. So many different kinds of alternate functions. How do we sort that out? Well, internally there's this idea of a multiplexer, and so there's a list of alternate functions for any given pin. Not every pin will have all these functions, and not all functions are, the list can vary from pin to pin. But this is kind of the general idea, is that there's a lot of different choices for what to do with a particular pin, what the alternate function is. And so in this particular slide, it gives an example of how do I select an alternate function. And it's setting it up so that I will do timer 3, which is this particular alternate function. So think of this as alternate function 0, alternate function 1, this is alternate function 2, which is why when you look at the code, it says, oh wait a second, right here. I want alternate function 2. I circled the wrong 2. This 2 was to set it up in alternate function mode. So the first few lines is, let's set up the pin to be in the right mode, to be in alternate function mode. And then after I set it up in alternate function mode, then I gotta figure out which alternate function I want. And there's 2 alternate function registers. There's register 0, which deals with these pins, and register 1, which deals with these pins. And so, depending on which pin you want, you need to be working with the correct register, and then setting up the pattern appropriately. Some registers that we've seen before, this is not new, this is just review. Of course, because we're dealing with timers and counters, we're gonna make sure that the counter is enabled, that substance has to be turned on. Remember, this is a low power device. You could really save energy by turning off the things that you don't need. And so the default is that we're gonna, most systems are shut off, so we need to make sure that things are on. If your stopwatch is working, you must have turned this on. If it's not working, maybe this is one of the reasons. If your stopwatch is working, that means you are updating the 10th digits correctly. Okay? You wrote in the interrupt service routine, and it's going to be triggered by a interrupt flag, and you dealt with this flag already. So this is, again, nothing new. Now, when this timer overflows or goes over that capture compare register, CCR, it's going to flag it and say, hey, I'm changing state. And so there's a series of bits here. Depending on which timer you use, it's going to turn on a particular flag. Now, our particular timer that we recommend to use this week only has this particular flag. So you may choose, if you want to monitor that flag. But the whole point, really, I think, of using a programmable timer is to be able to just set up the thing and walk away and not have to monitor it. But that flag is available for you to use if you want to. This past week, you've been using the interrupt from the timer to produce an interrupt service routine trigger the interrupt service routine. But in order to let that interrupt go through, there was an interrupt enable that had to be enabled. You may recall there was a block diagram that showed these 2 bits running into an AND gate. The flag, just because the flag is on doesn't mean that I really got an interrupt. It has to be ANDed with an enable bit. If that is 1, then that flag can get through to the interrupt system, going through the nested vector interrupt controller, so on and so forth. Again, this is not new. If you've got your stopwatch working, you've got these things going on. Okay? Let's talk a little bit about the capture compare register. It's the new register that's going to be added this week. We're going to basically compare the counter to that register, and once the counter equals that register, we change state. Okay, that's the basic idea. Again, there's different modes. You could use it in a few weeks. We'll do this. We're going to monitor a pin, and when something happens on that pin, we're going to time it. That's called input capture mode. You can produce an output, a signal. Okay, and but what we're going to do is we're going to use this mode, which is called PWM mode. And so whenever the count is less than CCR, we're going to say we're active, but as soon as greater than or equal, we go to inactive. Let me back up a few slides, kind of review where we are in the system of things. Okay. I talked about auto reload, capture compare register, the counter is running, it's monitoring these 2. Okay. Every time it reaches this value, it changes state, changes the pulse width. Every time it reaches that value, we start all over. Okay? Now I want to turn my attention a little bit to the bits you got to deal with in this register. We're going to send the signal to the output, but we want to use it in PWM mode. So there is a register, CCMR1, Capture Compare Mode Register, and that's this one. The Capture and Compare Mode Register is a little bit, this chart is a little bit difficult to understand. You got 8 bits here, but if you're in input mode, you read these bits. This is the definition. But if you're in output mode, you use this definition. So that's what this table means. We're going to be in one of the output modes, and so we don't look at this second row here, we look at this row. Okay? And we get to choose which PWM mode do we want to use. We're going to switch from active signal to inactive signal, or from inactive signal to active signal. Okay? Plus, we can also define whether active is active high or active low. So it's kind of redundant. There's basically, you could say there's more than one way to skin a cat. I can go from active high to inactive, or I can go from inactive low to active high. So they're really the same thing. It kind of depends on which way you want to speak. But you need to choose a mode and get these bits taken care of. Okay? Later on, we'll talk about these bits over here, how we will use these to do, just like what's going on with the input. An event's going to happen, we're going to use that pin to watch the world, but we don't have to worry about that today. The default on reset is it's going to be 0, it's going to be an output mode. Backing up again, there is, I said, we can choose going for PWM mode, we have to choose whether we're going from active to inactive or inactive to active, but here we can also swap the polarity. We're going to say, well, active is actually active low, or active is active high. So you see, you get back to where you were again by switching the polarity. It's like 2 minus signs make a plus sign when you multiply them together. That sort of idea. So the output polarity has to be chosen in the Capture, Compare, Enable register. So that's the next register I want to take a look at, and that's this one. Okay. Capture, Compare, Enable register. On reset, it's all zeros. And so you can read what all zeros mean. Okay. So we're going to focus our attention on this bit and this bit. Now, this register is also appearing right here. So it affects the polarity, but it also determines whether the signal will even get out to the pin. So that's this flag. All right? So a lot of little bits to deal with. Let me kind of back out a little bit again and just try to summarize again what are the main registers that have to be dealt with. You're going to determine the period by setting ARR correctly, as well as the prescaler. I didn't want to complicate the slide by adding the prescaler in here, but you already know how to deal with the prescaler and auto reload register. This week we add Capture Compare register. Make yourself a table. Button 1 equals CCR equal to this. Button 2 equals that. Okay, make yourself a table. And when you match buttons, hopefully these duty cycles will change. Okay, here's some examples again, kind of belaboring the point maybe. Here we have, in all the cases, auto reload register is equal to 8. Remember, the count starts at 0, so 0 is a time period as well. So it's really 9 counts. Goes from 0 to 8, and then starts all over again when we hit ARR equal to 8 on the next count. So all these waveforms basically start all over again at ARR equal, when count equals ARR equal to 8. But in between, we can change the capture control register. Here, the capture control register is 4, and so the moment the count turns to 4, this flag, it's not the interrupt flag, but it's the capture compare flag. It says, hey, I'm changing state. Okay. And the state changes. In this case, it's going from active to inactive. This is an example of what happens when the capture control register is equal to 8. In other words, it's equal to the auto reload register. It's on most of the time, and when the count reaches 8, it switches. And then the counter overflows to start all over again. In this particular case, I set the capture control register to a number bigger than 8. Well, the count will never reach a number bigger than 8, which means the output will always be active, and the capture compare flag will always be high. On the other hand, if I set the capture control register to 0, then the output will always be 0. It's always inactive. And I satisfied going over this number, and so again, the flag goes up. Right? So this is an example of setting up timer 4, channel 1, to produce a PWM signal at 10% on this particular pin. Okay, so you can step through this and see all the different things that have to be adjusted. So here he calculates what the period is. It involves the auto reload register, the number. Remember, it's +1. The duty cycle involves the capture compare register. Got to configure the bits, make it an output, choose a mode, okay? Enable the output to be driven, okay? Decide what the polarity is going to be, okay? Choose alternate function mode, because we're going to use that port as an alternate function mode, and then select which alternate function mode you want. You want the PWM alternate function mode. Now we're going to do this week for our particular port. We're going to use PA6 instead of PB6, and we're going to use timer 10. So this is kind of a pattern. Okay, so this is an assignment this week. Let's generate a PWM signal using timer 10. The period should be a 1 millisecond switching frequency of 1 kilohertz. And try to generate 10 different duty cycles using the buttons 0 through A. 0 means shut off. Okay? And when it's off, it should be active, inactive. Use your oscilloscope to measure the duty cycles, see if they're accurate, and then time permitting, try to see what needs to be done to generate a PWM signal at 100 hertz, which is slower frequency, and also at 10 kilohertz, which is higher frequency. So the question is, what would need to be changed? How much change you had to do to redo everything for a different PWM signal? Okay, any questions? Okay, seeing none, have a good week. We will see you